In the wooded hills of southern Ohio, scientists deliberately set fire to an oak forest that was already in trouble. Then they came back and burned it again, and again, and again. To anyone watching flames crawl through the fallen leaves, the plan could look reckless. The great oaks above were aging, young oaks were almost missing below, and now researchers were adding fire to a forest that seemed to need protection. But after 2 decades, the burned ground revealed something the untouched forest could not. Young oaks and hickories were preparing to replace the old canopy, native woodland plants were returning, and the forest was becoming more diverse. The fire had not destroyed its future. It had exposed why that future was disappearing. The strange part was that the forest did not look like it was dying. Walk through Zaleski State Forest, Tar Hollow State Forest, or the Vinton Furnace landscape in southern Ohio, and mature oaks still tower over the ridges. White oak, chestnut oak, and black oak form a broad roof above the steep ravines. Hickories stand among them. In autumn, the canopy still turns copper, red, and gold. Yet a forest is more than the trees currently overhead. Its future is waiting underneath them. When researchers looked below the canopy, they found a warning. The next generation did not resemble the one above it. Young red maples, sugar maples, and other shade-tolerant trees were filling the middle and lower layers. Oak seedlings were present in places, but too few were becoming large enough to inherit the canopy. The old oaks could survive for decades, perhaps much longer. But when storms, insects, disease, and age eventually opened gaps, maples were positioned to take their place. The oak forest was not collapsing in a dramatic wave. It was quietly becoming a different forest. Ecologists call this process mesofication. The word sounds technical, but the mechanism is simple. A darker, damper forest favors trees that tolerate shade and moisture. Those trees produce leaves that often hold moisture and burn less readily than dry oak litter. Fire becomes less likely. The understory becomes even shadier, and oak seedlings lose more ground. It is a feedback loop. Shade encourages the trees that create more shade. Moist litter discourages the fire that once interrupted them. The forest gradually engineers conditions that work against oak. This raises an obvious question. If oak was already the dominant tree, why could it not simply reproduce beneath itself? Oak seedlings can endure years of hardship, but they eventually need light. They invest heavily below ground, building root systems that store energy. That strategy helps them recover after injury. It does not help them outrun a maple sapling in permanent deep shade. Maples can wait beneath a closed canopy and grow when even a modest opening appears. Oaks usually need a larger disturbance, enough to reduce competitors and send sunlight toward the forest floor. Without that disturbance, a tiny oak may survive, but survival alone does not create the next canopy. For centuries, disturbance often arrived as fire. Fire scars preserved in trees and charcoal preserved in soil show that flames were once a recurring part of many eastern oak landscapes. Some fires began naturally. Many were deliberately set by indigenous people, and later burning was connected with farming, hunting, railroads, charcoal production, and other land uses. At the Ohio study sites, evidence from fire scars showed that fire returned roughly every 8 to 15 years from the late 19th century into the early 20th century. Then organized fire suppression expanded during the 1930s, and the flames largely disappeared. That policy came from an understandable place. Wildfire had killed people, destroyed towns, and stripped landscapes. Fire was treated as an enemy that should be extinguished as quickly as possible. But low-frequent surface fire and an uncontrolled crown fire are not the same ecological event. One can creep through leaf litter while mature trees stand above it. The other can race into the canopy, kill large trees, and threaten entire communities. When all fire was removed, the quiet surface burns vanished too. Oak seedlings lost one of the disturbances they were adapted to survive, while thinner-barked competitors gained decades to establish. By the end of the 20th century, managers faced a forest that still wore an oak canopy, but was losing its oak future. They could see the problem. What they did not have was a clear 20-year experiment showing which treatment could reverse it. So in 2000, the Ohio Hills Fire and Fire Surrogate study began. The experiment occupied 3 locations across the southern unglaciated Allegheny Plateau. The land is folded into narrow ridges, steep slopes, and damp ravines, which meant the scientists were not studying one uniform forest. A dry, south-facing ridge could respond very differently from a shaded hollow only a short distance away. Each location was divided into 4 treatment areas. One was left alone as a control. A second was partially harvested, reducing the density of trees by about 30%. A third received prescribed fire. The fourth combined partial harvesting with fire. This design allowed the researchers to ask a deceptively important question. Was fire itself necessary, or could people reproduce its useful effects with chainsaws and logging equipment? Mechanical thinning could open the canopy and remove competing trees. It could also reduce density without smoke, escaped fire risk, or blackened trunks. If cutting alone produced the same result, managers would have a substitute for fire. The burn crews worked in early spring, when many plants were dormant and conditions could be controlled. These were not raging wildfires. Small flames moved across fallen leaves and fine branches near the ground. Crews monitored weather, fuel moisture, and fire behavior, while prepared boundaries contained the burn. The first fires were lit in the study's first year. More followed around years 5, 10, and 16. 4 burns were spread across a study that continued for about 2 decades. That timing matters. The scientists did not spend 20 years continuously torching the same trees. They returned periodically, allowing the forest to respond between burns. The treatment was closer to restoring a missing rhythm than applying constant destruction. After the flames passed, the landscape did not instantly transform. Some saplings were killed above ground, but resprouted from their roots. Fallen leaves accumulated again. Tree mortality continued for years in places, especially where early burns had been more intense. The researchers kept measuring. They recorded canopy structure, saplings, seedlings, ground layer plants, leaf litter, fine fuels, and large fallen wood. They compared dry ridges with intermediate slopes and moist sites. Most importantly, they could compare every treated area with forests that had been left untouched. Early results suggested that fire was changing the understory. But a few seasons can be misleading. A flush of wildflowers may disappear. A top-killed maple may grow back. Oak seedlings may emerge without ever reaching the size needed to survive the next disturbance. Only time could reveal whether the experiment had changed the forest's direction. After roughly 20 years, the answer emerged. Repeated prescribed fire reduced the density of shade-tolerant, fire-sensitive trees in the sapling and mid-story layers. It opened the structure of the forest and interrupted the feedback loop that had favored maple. Then came the result managers had been waiting for. Large oak and hickory regeneration increased substantially on dry and intermediate parts of the landscape. These were not merely fresh sprouts that might vanish next season. Advanced regeneration means young trees already established before a major canopy opening. Their roots give them a head start. When an old tree eventually falls and sunlight pours through the gap, those young oaks and hickories are ready to respond. The untreated forest still had mature oaks overhead, but the burned forest had improved the odds that oaks would remain after those veterans were gone. And the biggest visual change appeared much closer to the ground. With fewer saplings crowding the understory, more sunlight reached dormant seeds and low-growing plants. Fire also exposed patches of mineral soil. Across dry, intermediate, and moist sites, the ground layer became more diverse. Native perennial herbs increased, and burned plots developed plant communities distinct from those in the untreated forest. The ash did not magically manufacture a woodland. Fire removed part of a biological bottleneck. Plants already present as roots, seeds, or scattered survivors finally had room and light to express themselves. That distinction is important because the popular image of a healthy forest is often a landscape packed with trees. Dense vegetation looks abundant. Open space can look damaged, but an eastern oak woodland can support layers of grasses, sedges, ferns, and wildflowers beneath widely spaced trunks. When maple saplings form a dark wall, that ground community can disappear, even while the total number of stems increases. The prescribed burns traded a crowded, uniform understory for a more varied structure. Patches of light appeared, herbs returned, young oak and hickory gained size, different heights and openings created more kinds of habitat. If this experiment ended there, the conclusion would be easy: burn the forest and the oaks return. But the untreated controls exposed only half the story. The mechanically thinned areas exposed the other half. Cutting trees changed forest structure, yet mechanical treatment alone did not reverse massification over the long term. Opening the canopy once was not enough. Shade-tolerant competitors remained capable of returning, and the ecological filter created by repeated fire was missing. The areas that received fire, with or without partial harvesting, moved more clearly toward oak and hickory regeneration. That result suggested fire was doing more than removing a certain amount of wood. It was selecting among species according to how they survive damage, resprout, use light, and compete over repeated cycles. Oaks have traits that fit that filter. Their bark becomes protective as they mature. Young oaks can store energy in large root systems and resprout after their stems are top-killed. Many competing saplings have thinner bark or lose more ground when fire repeatedly resets their above-ground growth. One burn may injure both. A recurring fire regime changes the competition. Topography then complicated the result. Fire generally burned more intensely on dry sites, where fuels dried faster. Those areas experienced stronger reductions in mid-story competitors and, in some patches, greater mortality among overstory trees. The resulting openings helped oak regeneration, but they also created costs. On moister sites, fire intensity was often lower. Even there, repeated burning increased ground layer diversity and reduced shade-tolerant competitors. The treatment worked across the landscape, but it did not produce identical results everywhere. This was one of the study's most useful findings. A prescription written for a dry ridge cannot simply be copied into a damp ravine. The same ignition pattern can meet different fuel moisture, wind exposure, slope, and vegetation. Fire is not a paint roller. It moves through a landscape according to the landscape itself. The experiment also revealed a result that refuses to fit an inspirational ending. The burns reduced fine surface fuels immediately. Before the fire, in year 16, fine fuel levels had largely recovered during the 6 years since the previous burn. That fire consumed about half of the fine fuel measured before it. Large woody material behaved differently. Early burns intentionally caused elevated tree mortality on some dry sites to create canopy openings. As those dead trees fell, large logs accumulated. The later fires consumed less than 1/10 of that heavy wood, so while fine fuels declined for a time, large woody fuels increased in some places. During severe drought, that material could contribute to dangerous fire behavior. Prescribed fire had improved oak regeneration and plant diversity, but it had not erased risk. It had redistributed it. Managers would still need to monitor dead wood, adjust burn intensity, and decide how much overstory mortality a particular site could tolerate. That caveat protects the science from the headline. These researchers did not discover that every forest should be burned. They showed that periodic, carefully managed fire can help sustain eastern oak systems that developed with repeated surface burning. Some forests are naturally too wet to burn often. Some contain species or soils that can be damaged by an inappropriate fire. Smoke can harm nearby communities. Burns can escape. Drought can turn a safe prescription into a dangerous one. And a forest already weakened by excessive deer browsing may lose oak seedlings if they do not have enough stored energy to re-sprout. Fire must match the ecosystem, the weather, the topography, and the goal. The Ohio experiment also should not erase the human history behind these landscapes. Long before prescribed fire became a modern forestry tool, indigenous communities used burning to shape travel routes, food resources, hunting grounds, and plant communities. The open oak landscapes, later described as natural, were often influenced by generations of human decisions. Suppressing fire did more than stop a physical process. It removed a relationship between people and land, then treated the resulting dense forest as a timeless baseline. Now, managers are relearning what the tree rings had already recorded. Oaks did not dominate simply because nobody disturbed them. In many places, they endured because disturbance returned often enough to prevent permanent shade from taking control. That lesson reaches far beyond southern Ohio. Across the eastern United States, mature oak forests support insects, birds, mammals, and people. Acorns feed deer, turkeys, squirrels, and many other animals. Oak leaves and bark support immense food webs. The wood has cultural and economic value, yet a canopy full of old oaks can conceal a future in which oak becomes scarce. Consider what happens during an acorn crop. In a good year, the forest floor becomes a pantry. White-tailed deer, wild turkeys, mice, chipmunks, and squirrels collect the falling mast. Some acorns are eaten immediately, others are carried away and buried. A fraction escape, germinate, and extend the forest into another generation. Those animals do not need every tree to be an oak. A mixed forest is valuable precisely because different species provide food and shelter at different times. But when oak steadily disappears from the future canopy, the ecosystem loses one of its major pulses of autumn food. The change also reaches creatures many visitors never notice. Caterpillars feed on oak foliage, birds feed those caterpillars to their young, and predators feed on the birds. Fungi exchange nutrients with oak roots. Cavities in old trunks become shelter. Loose bark, fallen branches, and decaying logs create small worlds within the larger forest. This is why regeneration is not simply a timber question. Replacing an oak canopy with a dense layer of shade-tolerant trees changes light, leaf litter, fire behavior, seasonal food, and habitat at the same time. It also explains why scientists looked beyond tree counts. A treatment that produced young oaks while erasing the ground flora would be an incomplete victory. A treatment that created wildflowers for 2 seasons but failed to establish future canopy trees would be temporary. The long experiment tracked several layers because a forest can improve by one measure and decline by another. Repeated fire produced a combination that mattered. It favored larger oak and hickory regeneration on much of the landscape, while increasing native perennial herb richness across site conditions. In other words, the same treatment helped prepare tomorrow's canopy and released life at ankle height. That does not mean every response was positive or every species benefited. Open woodland habitat favors some animals, while dense, moist forest favors others. Creating a patchwork rather than treating every acre identically can preserve more of those needs. The goal is not to force one perfect forest across the hills. It is to restore enough variation that the landscape is no longer trapped on a single path. The disappearance may not begin with dead trees. It can begin with missing seedlings. That is why the scientists kept watching for 2 decades. A forest operates on a timescale that makes quick success easy to fake. Cutting can create instant sunlight. A burn can produce a dramatic spring bloom. Neither proves that a young oak will survive long enough to replace a tree that may stand for another century. The Ohio Hills study could not wait for an entire new canopy to mature, but it could measure whether the ingredients of succession had changed. After repeated fire, there were fewer mesophytic competitors, more large oak and hickory regeneration on suitable sites, and richer communities of native perennial plants across the landscape. The forest had not been reborn from total destruction. Its path had been redirected. That may be the most surprising thing that rose from the ash. Not a sudden wall of trees, but options. An oak seedling with enough root energy to claim the next opening. A woodland herb receiving sunlight after decades in shadow. A patchwork of dense and open habitat instead of one dark layer. A forest with a better chance of remaining an oak forest after the old giant's fall. The flames were only minutes high. The response took years. Return to those Ohio ridges today and the mature canopy can still make the burned and unburned forests look similar from a distance. The real experiment is underneath. One plot carries more of the same shade-tolerant saplings. Another carries young oaks, hickories, herbs, and the evidence of repeated surface fire. One shows the forest as it is, the other reveals what it may become. For almost a century, protecting forests often meant keeping every flame away. The Ohio Hills experiment showed why protection can sometimes require a more difficult kind of care. Crews must choose the right day, control the edges, accept temporary black ground, and keep measuring long after the smoke disappears. Fire was not a cure delivered once. It was a process restored carefully enough for the forest to answer. And after 20 years, the answer was growing beneath the old oaks. If you want to see another landscape where the most dangerous-looking solution became part of its recovery, click the documentary on screen.